minute here. There's several days in here. A couple things I need to say. There's several days, several units that are multi-day units, like Friday, Monday, 3.3, 3.3, day 2. Tuesday, block day, 3.4, 3.4, continued. Curve sketching, day 2. And so we try to slow it down because this is really, really important stuff. It's not really that it's hard, it's just that it's important and it forms, I guess as it all does, a basis of what we do the rest of the year. So we try to slow it down on this. Second thing I need to say about this throws people off. When this says first derivative test, second derivative test, those are not like summative assignments. That's the name of the process in calculus. There's a first derivative test to see if something is whatever. Okay? So it's a good thing I didn't hand this out, because usually if I have it and hand out, people are like, wait a minute, we have a test on Friday and on Tuesday and then on the next block day? What's going on here? Like, no, that's the name of what we're learning that day, is the first derivative test and then the second derivative test. So those days are not summative assignment days. That's the name of the process, the name of the thing that we're learning. So that's always a fun point of confusion if I forget to say it. We have a test today? General speak before we jump into 3.1. All of this, I should have even labeled it on here. And by the way, I'll have copies of this for you tomorrow or Tuesday or Wednesday or sometime. This whole unit is applications of first and second derivative. So like using the first and second derivative. So we're not going to be learning any more first derivatives yet. There's a few more later on, but we've pretty much got the facts down. Like the derivative of sine is cosine, derivative of tangent is secant squared, the power rule, chain rule, quotient rule, all those rules. Now we're going to use those to do some other stuff. So it's a little bit of a shift. I don't know if it's a good shift or a bad shift, but you've got to know all the derivative rules, and now we'll use them to do a variety of other things. All right, let's start with 3.1, Extrema on an interval. Sounds fancy. I guess while you're getting stuff out and getting ready, what does extrema mean? Do you know? Or extremes? So not even in a calculus sense. What is it? What's an extreme? Oh, that is in a calculus sense. A max or a min. So these are the things like extremes in politics. You know, somebody on the far right or the far left, like way out there, one side or the other. Extremes on a graph would be the tops or the bottoms, the mins or the maxes. So we're talking about finding those today. The extreme value theorem. If f is continuous on A to B, continuous on a closed interval. We'll look at some examples that don't meet this criteria and why it's part of the criteria. So there's our if. If f is continuous on A to B, then f has both a minimum and a maximum. on A to B. In some ways, it seems like it's too easy. Like, so if there's a function that's continuous, so nothing crazy, on in this interval, then somewhere in there it's at its maximum, and somewhere in there it's at its minimum. That doesn't seem like too big a deal. Let's draw a picture to maybe illustrate. So from A to B, I need to draw a function that's continuous on the closed interval. So the endpoints need to be closed circles. I can't have open circles. It's got to be a closed interval. Draw something like that. Here's some terms that I don't know that we've used before. The absolute max, also known as the global max, like the overall max, is at x equals, so for this particular graph, where's the graph the highest? What x value? B. Good. That happens to be an endpoint, which is fine. How about the absolute minimum? Where is that? Absolute min at x equals D. That's not one of the endpoints, but that's okay. Now, that's what the theorem guarantees, that there's a max and there's a min. What's not part of the theorem, but what we need to talk about because it kind of throws people off, is that point at C. Something's going on at x equals C. Have we used a term to describe that yet? I don't know if we have or not. Like, it's some kind of maximum, right? Like it's like top of a mountain, but it's not the overall maximum. So we call that a relative maximum. Like, relative to the points around it, it's a maximum. Or a local maximum, as in his local area, he's at the top of a mountain. He's not the overall peak, but he is a peak. Let's back up a little bit and talk about the if part. If f is continuous on a closed interval. So let's draw one that's not continuous and see why it might not have a max or a min. So I'm setting out to intentionally break the condition, the if part of the statement. I want to draw something that's not continuous from A to B. So let's see. An asymptote would be not continuous. So this is like rule 1. This thing is not continuous. So we're not guaranteed to have a max or a min. It doesn't mean we won't have one. It just means we're not guaranteed to have one. In fact, there is a minimum. Where's the minimum? At B. Where's the maximum? Hint, it's kind of a trick question. You could kind of say infinity. But infinity is not really a number, so we would say there is no maximum. again, we failed the if part of the statement of the extreme value theorem, so we're not guaranteed to have a max and a min because this thing wasn't continuous. Right, the second part, the closed interval thing. So let's draw one that doesn't have a closed interval, meaning it's got an open interval. So open circles at A and B. Again, it doesn't guarantee that we don't have one. It just means you can't be sure that there is one. So this one has a minimum at x equals c. But at what x value is there a maximum? It's kind of a trick question because the maximum is like right close to b, but it's an open circle, so it never gets there. So you can't say the max is at b, and you can't say the max is, whatever this is, if it's 12, because it never gets to 12. It's like 11.999999, but it never gets to 12. So this does not have a maximum. Now you're right. There is a limit. The limit as x approaches b of this function is 12. That's at least from the left, because we don't know what's on the right. So yeah, the limit from the left would be 12. That's true. But that function never gets to 12 because of the open interval thing. So it's got to be closed interval, and it's got to be continuous. And if that's true, then there's definitely at least one max and at least one min. Like there could be a tie in which there'd be two of them. Number 2, critical numbers. Definition of a critical number. If f prime at c equals 0, or f prime at c is undefined, by the way, this feels like we're hopping around. It's like, okay, we talked about extreme values, now we're talking about critical numbers. We'll put them together in a minute. So if the derivative at c is 0, or if it's undefined, then c is a critical number. We'll use this idea a lot in the coming weeks and months even. And probably the thing that gets forgotten is the undefined part, because most of our problems, the derivative is going to be 0. That's going to be our critical number, but we have to remember to check for undefined places as well. Let's see. F prime is 0. See if we can draw what that would look like. So that's the slope of f at c is 0. So that'd be like right there. There's a horizontal tangent line. Get our brain back thinking here. What if f prime is undefined? What kind of tangent line would that be if f is undefined? If f prime is undefined? Vertical, yeah. I saw a couple of these going on. Slope is 0, it looks like this. If the slope is undefined, it looks like that. So a vertical tangent line would be something like that. where just for a moment it's going straight up. And you'd have a vertical tangent line. You can also have an undefined slope. Do you remember where else the slope doesn't exist or the derivative doesn't exist? What kind of point is going on? At a cusp, there's no derivative there. The derivative is undefined. Okay, now we're going to put these two ideas together. You got critical numbers where slope is 0 or undefined, and we've got extrema where there's maximums and minimums. So here's how we put those two ideas together. All relative extrema occur only at critical numbers. So if you got a relative extrema, you know that was a critical number. If you got a critical number, though, you don't necessarily have an extrema. It's like the squares and rectangles thing from geometry, right? All squares are rectangles, but not all rectangles are squares. All relative extrema are critical numbers, but not all critical numbers are relative extrema. And you can kind of see that from the pictures we drew here. That vertical tangent line was not a extrema. The other two were, though. So all relative extrema come from the critical numbers. If you got a critical number, it's not necessarily a relative extrema. For some, a Venn diagram might be helpful. The outer circle is the critical numbers. The inner circle are the relative extrema. So if you've got a relative extrema, you know you're in the land of critical numbers, but if you got a critical number, you may or may not be a relative extreme. A couple pictures of critical numbers that aren't relative extrema. Something like that. That has a slope of 0, but that's not an extrema. Or the vertical tangent line. We did that one already. Infinite slope or undefined slope, probably a better way to say that, but not a relative extrema. Here's why this matters. We're like, well, what we're concerned about is relative extrema. So it's like, well, why do we care about critical numbers? And the reason we care about critical numbers is that we can find them easier than we can find relative extrema. Find critical numbers because we can set the derivative equal to 0, or the derivative, I guess I shouldn't say equal to undefined. Not exactly correct. I should just say f prime undefined. So we know how to take a derivative, then we know how to set it equal to 0 or see where it's undefined. So that gives us our, like, okay, now we have some possible critical numbers. And then to find the relative extrema, we will test the critical numbers. So there's not like a magic way to jump straight to relative extrema. It's like our calculus can find us the critical numbers, and then we'll do something to sort through the critical numbers to see if they are relative extrema. So that's why we have to talk about both. We can't just jump straight to relative extrema. Although relative extrema is the goal, we have to go through critical numbers to get there. Let's do some examples. Let's find critical numbers for, well, let's just leave it at that. Find critical numbers, and we'll do several examples. So again, critical numbers is where f prime equals 0 or undefined. So let's say f of x equals x squared minus 7x plus 12. We'll get our brain back rolling here in calculus. Make sure you hadn't forgotten anything over the break. So Connor, x squared minus 7x plus 12, what's the derivative of that?
2x minus 7.
Good. You still got it. Nicely done. 2x minus 7 is the derivative. I want to know where that's 0 or where it's undefined. So 0 equals 2x minus 7. So x equals 7 halves. Where it's undefined, it's not undefined anywhere. Like, it's always defined. So this happens more often than not. Like, the undefined part doesn't really contribute anything, but we're going to continue to look for it because once in a while it does matter. And so that's it for critical numbers. Like, where's the derivative 0? Where's it undefined? That's it. So make sure you read the directions carefully, because if it only asks for critical numbers, like this one does, then we're done. We don't really know yet if that's a relative max or a min, or neither one. But we don't care about that yet. We're just looking for critical numbers. F of x equals 2x minus 3x to the 2/3. It's a little bit harder, but that's okay. We'll even split it up, although that means somebody gets the easy one and someone gets the hard one. Natalie, you got the hard one. Mark, what's the derivative of 2x? 2. Yeah, sometimes you get the easy one. Natalie, what do we think?
I don't know.
Well, it's the same process Mark used. It's a lot harder to do, but it's the same process.
Mm-hmm.
So what do I do with the 2/3? So just like we bring the 1 down and decrease the power by 1, bring the 2/3 down and decrease the power by 1. So what's 1 less than 2/3? What's 2/3 minus 1?
I don't know.
2/3 minus 1. You were close. 2/3 minus 1. So 2/3 minus 3/3 is negative 1/3. So clean this up a little bit. The 3's cancel. 2 minus, and I'm going to put that x to the 1/3 in the bottom since it has a negative exponent. Now I want to know where that's 0 and where it's undefined. It would be easier if this was one fraction. So I'm going to get a common denominator and add these together. So let's see, this first number would need a denominator of x to the 1/3, which means it also gets a numerator of x to the 1/3. And so now we think back, this is what we're doing in pre-cal right now, actually. What makes a fraction 0? What makes a fraction undefined? Well, a fraction is 0 if the top is 0. A fraction is undefined if the bottom is 0. And that's the two things we're looking for critical points. F prime equals 0 or F prime is undefined. So a little bit of algebra. Let's set the top equal to 0. A little bit more algebra here. So let's see, x to the 1/3 is 1. What does that mean x is equal to? How would I fix the 1/3? What would I do to both sides to cube both sides? And 1 cubed is 1. So x equals 1 is one of the critical numbers. That would be where the top is 0. Where the bottom is 0, kind of the same thing. If I cube both sides, I get x equals 0. So that one had two critical numbers. One made the derivative 0, and one of them made the derivative undefined. So applications of first derivative. We had to take a first derivative and then do something with it. Let's do one more because we've got to refresh our derivatives after the week off here. F of x equals 2 sine x minus cosine 2x on 0 to 2 pi. Let's take some more volunteers here. Emma, how about the derivative of 2 sine x?
No, I need to write it down.
Okay. Andrew, you're going to be up for derivative of cosine of 2x.
For the first part would be 2 cosine x times x.
So you're thinking chain rule?
No.
What's the derivative of x?
Oh,
1. So just 2 cosine x.
and then
Wait, Andrew's going to get the second part for us. Good. Plus sine 2x. And then Emma reminded us of the you had it down. You knew it before she said chain rule. I don't doubt it. So 2 cosine x plus 2 sine 2x. And we want to set that equal to 0 or see where it's undefined. I don't think it's going to be undefined anywhere because I know what cosine looks like. I know what sine looks like. They're never undefined, so I don't have to worry about that. I want to see where it's 0. There's a trick to this one, and it would help if we knew what sine of 2x equals. I don't expect anybody to remember that. That's a pre-cal thing from way back. But sine of 2x is 2 sine x cosine x. So that's like a little side note that another pre-cal, like everyone remembers, well, I shouldn't say that. I hope everybody remembers sine squared plus cosine squared is 1. We use that one a lot. We still need to know that one. This one, much less often. It's sometimes helpful. it must be necessary in this homework assignment, which is why we're doing this one, or doing this example to remind us of this. So in place of sine 2x, I'm going to put 2 sine x cosine x. So I'm still algebra. Okay, enough algebra here. I want to set that equal to 0. What could I factor out from each of these? Yeah. I can factor out a 2 cosine x. I had 2 terms to start with, so I'll have 2 terms to finish with. Nikita tried to write her name so small I wouldn't read it, I guess. Nikita, on that first term, when I take 2 cosine x away from 2 cosine x, it would be 1. Good. And in some ways that's the easier one, but in other ways people forget that when they're like, oh, you took it away, it's gone. Like, well, no, it's not gone. You need a 1 there to kind of hold the spot. Tierney, how about in the second blank? If I take a 2 cosine x, what's left? 2 sine x. And now I've got 2 things that are multiplied to equal 0. So either the first thing is 0 or the second thing is 0. Let's do a little pre-cal review on this one. So let's see, cosine of x equals 0. That would be, cosine is the x-coordinate, so that would be at those 2 spots. Look at everybody called on today, maybe. So, Lauren, where's the cosine equal to 0? Good. See, for the other one, we move things around, we get sine of x equals negative 1/2. So I'll draw the picture, Emily, to help you out. So what angles have a sine of negative 1/2?
Well, it's negative pi over 6, right? But that's
Good, yes, it is negative pi over 6, but we want to give answers between 0 and 2 pi. So what would be the other way to say that? So, I mean, that's negative pi over 6 isn't wrong, it's just not the answer I want to give. So how do I get there the long way around? Somebody help her out. What's the long way around? 11 pi over 6.
I have to count like every time. I don't want to spend so much time with that.
Sarah, what's this other one over here? 7 pi over 6. So there's our 4 critical numbers. But the bulk of that problem wasn't really about critical numbers, it was about pre-cal. Oh, good question. So f prime undefined nowhere. So I already did what I warned would be our habit. A lot of times we don't have to worry about the undefined one, and so we forget to look for it, and then it's going to sneak up and we'll miss it because we're not looking for it. All right, what we haven't done yet is to narrow down from our pool of critical numbers, that's sort of our possible extrema, to narrow it down and find what the extrema are. But that's really an easy final step here. So let's do one of these. Find the extrema And if it doesn't specify, it means absolute. If it wants relative, it has to ask for relative. So find the absolute extrema of that function between -2 and 2. Well, again, there's no magic way to jump straight to the extrema. Our job is to find critical points and then figure out what to do with those critical points. So let's first find critical points. F prime. Let's see. Izzy, I don't have a popsicle stick for you yet. What's the derivative of F?
12x cubed.
Keep going.
Minus 12x squared.
Good. So we'll set that equal to 0. We can factor out a 12x squared, and that would leave x minus 1. So x equals 0 and x equals 1 are the critical points. That doesn't mean they're extrema, but it means they might be extrema. So here's how we go from critical points to extrema. We'll test our critical points on a table of values. With the endpoints, though. That's with endpoints. I can guarantee you there's going to be a question on the test that uses the endpoints and someone's going to miss it because they didn't check the endpoints. So we're going to check 0 and 1 and the endpoints on a table of values. So just like super old school, old fashioned, I've got some values to check, 0 and 1, but my endpoints are -2 and 2. And just whoever's the highest is the max and whoever's the lowest is the min. It's like at that last step from going from critical points to extrema is the easy part. We're short on time, so I'll just tell you that f of -2 is 80 if we plug it in. F of 0 we can do quickly. That would be 0. F of 1 is not difficult either, -1. F of 2 would take a little bit of work and we get 16. So there's an absolute max at, well, let's be clear here. The max is at, what's the x value? At -2. And the absolute max is, so what's the maximum value of the function? So it occurs at -2, but what is the maximum? 80. So be careful about the instructions. Where is it versus what is it? And on a free response question, though, the safest way to go is to just give the point, because then you covered both. So free response, you can kind of sneak your way around it and just give the point. Multiple choice, be careful about where is it versus what is it. Because where is the x value, what is the y value? So you answer those two questions, and then we'll make sure we're on the same page here. The absolute min. So where is the absolute min at? What's the x value of the absolute min? Is it x equals 1? And what is the absolute minimum? -1. Again, the cheap way around it, not the cheap way around it, probably the smart way around it, is to answer with the point. That way you're not so concerned about who's the what, the where, just give the point. again, the goal is to find max and mins. That's kind of the point of today's lesson. But to get there, you have to go through critical points, put them on a table of values, then you can identify the extrema. So the goal is extrema, but you can't really jump straight there. Critical points, f prime is 0 or undefined. Then make an old-fashioned table of value, and then pick out who's biggest and who's smallest. So the last step's the easiest, like what's the biggest number, what's the smallest number. Getting there is maybe the tricky part, finding a derivative, setting it equal to 0. All right, the assignment's page 167, 1 through 45, EOO. Have we done EOO in here before? Every other odd. Again, it's a way to cover a large span of problems without assigning a ton of them. So 1, skip 3, 5, skip 7, so on. And of course, if you mess one of those up, then you end up doing the wrong set of odds. It's still good practice, so it wouldn't be that big a deal, but we'll find out tomorrow when you ask me to do number 11 and someone says, wait a minute, we didn't have to do number 11.